Welcome everyone. I'm Ralph Clayton, host of the VTM Podcast. This is episode 24. Today, I want to take you into one of the most important frontiers at the edge of computing. Light and quantum technology, nanophotonics, optical AI computing, light on chips, quantum dots, single photons, displays, biomedical imaging, sensing, and the possibility that the future of intelligence may not move only through wires, but through carefully controlled light. This is not simply a story about faster computers. It is not simply a story about brighter screens. And it is not only a story about making chips smaller, denser, and more efficient. At its deepest level, this episode asks one dangerous question. What happens when civilization begins to compute with light? Because for most of the digital age, computation has belonged to electrons. Electrons move through wires. Transistors switch on and off. Memory stores charge. Processors perform logic. Signals travel through copper traces. Data moves from chip to chip. Servers fill rooms. Data centers consume power. Cooling systems fight heat. And the world calls this progress. For decades, progress meant making transistors smaller. More switches on a chip. More operations per second. More computation in the same space. This was the age of Moore's law. The age when shrinking the machine gave the world more power. But that age has changed. Transistors are now unbelievably small. Wires are crowded. Chips run hot. Memory is expensive to reach. AI models grow larger. Data centers consume more electricity. And the old method of progress is running into walls. Not one wall. Many. The transistor wall. The memory wall. The interconnect wall, the energy wall, the heat wall, the cost wall. Artificial intelligence has made these walls harder to ignore because AI is hungry for a particular kind of computation. Matrix multiplication, tensor operations, large streams of numbers multiplied, added, transformed, normalized, moved, stored, and moved again. A modern AI model is not only a piece of software. It is a mathematical factory. It consumes numbers. It produces numbers. And the power cost is not only in calculation. It is in movement. Moving data from memory to processor. Moving data between chips, moving data across boards, moving data between racks, moving data across data centers. In the AI age, the wire has become a bottleneck. The distance between chips matters. The bandwidth between processors matters. The energy per bit matters. The latency matters. The heat from moving information matters. That is why light has returned to the center of the conversation. Not as a metaphor. Not as poetry. As hardware. Photons instead of electrons. Optical links instead of copper. Waveguides instead of wires. Modulators instead of electrical switches. Interference instead of conventional arithmetic. silicon photonics, nanophotonics, optical neural networks, photonic accelerators, quantum dot light sources. The old dream of optical computing is becoming urgent again because AI has changed the scale of the problem. This is the first lesson. Light is not being explored because it is beautiful. It is being explored because electricity is becoming expensive in all the wrong places. Electrons are excellent for logic, memory, and control. They have given us the modern world. But electrons interact strongly. They heat wires. They face resistance. They require charging and discharging capacitances. They lose energy as systems scale. Photons are different. Light can travel at high speed. Different wavelengths can share the same physical channel. Optical signals can carry enormous bandwidth. Photons can pass through one another without interacting in the same way electrons do. And when used well, light can move information with less heat and less loss over distance. This is why fiber optic communication already dominates long-distance data transport. The Internet's backbone is full of light, across oceans, across continents, between data centers, inside telecom networks. Light already carries civilization's messages. The harder question is whether light can move closer, from long-haul fiber into data centers, from data centers into racks, from racks onto boards, from boards into chip packages, from chip packages onto the chip itself, and then even deeper. Can light not only move information, but compute? That is the heart of optical AI computing. At first, the easiest role for photonics is communication. Optical interconnects, getting data from one processor to another. This matters enormously for AI clusters. A large model may be spread across thousands or tens of thousands of accelerators. Those chips must exchange information constantly. If communication is slow, the whole system waits. If communication consumes too much power, scaling becomes harder. If copper reaches its limits, optics moves closer to the processor. This is why packaged optics has become such an important phrase. Instead of keeping optical modules far away from the main chips, engineers bring optical communication closer to the computing silicon. The goal is to reduce electrical distance, reduce power, increase bandwidth, improve signal integrity, make AI clusters larger and more efficient. This is not yet the full optical computer, but it is the first invasion of light into the heart of AI infrastructure. The machine still thinks mostly with electronics, but it begins to speak with light. Then comes the second possibility. Use light to perform some of the mathematics itself, especially linear algebra. A neural network is full of weighted sums, inputs multiplied by weights, signals combined, vectors transformed by matrices. These operations can be mapped in certain architectures onto optical systems. Light waves can interfere. They can be split, delayed, phase-shifted, modulated, detected. A photonic circuit can be arranged so that the physics of light performs part of the computation as the signal passes through. This is the seductive idea. Do not compute by making every multiplication a long sequence of electronic switching events. Let the wave do the work. Let interference become arithmetic. Let propagation become processing. Let light moving through a chip become a mathematical operation. That is why nanophotonics matters. Because controlling light on a chip is not simple. Light has a wavelength. It does not like being squeezed into spaces much smaller than itself without consequences. It leaks, scatters, interferes, couples, absorbs, and yet, by shaping materials at the nanoscale, engineers can guide it. They can make waveguides, rings, resonators, gratings, metasurfaces, photonic crystals, modulators, couplers, splitters, detectors, nanostructures that control where light goes, how fast it moves, what phase it carries, what wavelength it occupies, and how it interacts with matter. Nanophotonics is the art of making light obey architecture at tiny scales. That is its power and its difficulty, because optical computing does not become practical just because light is fast. Many things are fast in a laboratory and useless in a system. A useful AI computer needs precision, programmability, scalability, memory access, error control, manufacturing yield, software integration, thermal stability, packaging, repairability, cost, and compatibility with the rest of the computing stack. That last part is crucial. No optical AI chip lives alone. It must connect to electronic control, electronic memory, digital logic, software frameworks, data center networks, power delivery, cooling, manufacturing supply chains, and the AI models people actually want to run. This is why optical AI computing has spent years between promise and practicality. The physics is exciting. The system is unforgiving. Early optical neural networks often worked on simplified problems, or with limited precision, or with demonstrations that were impressive scientifically, but far from the demands of real AI. That is changing, but slowly. Recent work has shown photonic processors running more advanced AI workloads with much better precision than earlier systems. That matters, because AI does not only need speed, it needs numerical reliability. If an optical processor rounds away small values, accumulates noise, drifts thermally, or cannot maintain precision across a large model, then its speed becomes irrelevant. A fast wrong answer is not acceleration, it is failure. That is the second lesson. Optical computing must earn the right to be called computing. Not only light moving through a device, not only a beautiful interference pattern, not only a benchmark chosen because it flatters the system. Real workloads, real precision, real integration, real energy accounting, real comparison with electronic accelerators. This is where the field is maturing. The question is no longer simply, can light compute? The question is, can light compute accurately enough, cheaply enough, and at large enough scale to matter? And even if the answer is yes, it may not replace electronics. That is another important point. The future may not be optical computers instead of electronic computers. It may be hybrid systems. Electronics for memory, logic, control, and programmability. Photonics for communication and certain high-throughput mathematical operations. Optics for moving data across bottlenecks. Electronics for storing, scheduling, correcting, and controlling. A future AI processor may be less like a replacement and more like an alliance. Electrons and photons, each doing what they do best. The photon carries bandwidth. The electron carries logic. The photon moves with low loss. The electron switches with mature precision. The photon performs parallel linear operations. The electron handles nonlinearities, memory, and decision. That hybrid future may be more realistic than the fantasy of an all-light machine replacing every chip. Because in computing, victory usually belongs to systems, not isolated miracles. This brings us to one of the most important limitations. Memory AI is not only computation. It is also access to data and weights. A model's parameters must be stored somewhere. Activations must be stored and retrieved. Training requires gradients. Inference requires moving weights quickly. Long, context models create enormous memory pressure. If an optical processor can multiply matrices quickly, but cannot access memory efficiently, the system bottleneck moves. The light is fast. The data is late. That is not a revolution. It is a traffic jam with better roads on only one block. So optical AI computing must solve not only the compute unit, but the data movement problem around it. This is why photonic interconnects may become important sooner than fully optical computation. Moving data is the pain point, and optics is already excellent at moving data. Co-packaged optics, silicon photonics, optical I/O, and wavelength division multiplexing may become the first large-scale commercial wave. Then, over time, more computation may move into photonic domains. That is a plausible sequence. First, light connects the AI factory. Then light enters the package. Then light performs selected operations. Then hybrid photonic, electronic AI systems become part of the computing landscape. Not all at once. Layer by layer. This is the third lesson. Technological revolutions often arrive first as infrastructure, not as spectacle. A user may never know that an AI model ran partly through optical interconnects. A scientist may not know that photons moved data between accelerators. A medical researcher may not care whether a matrix multiplication used interference on a chip. What matters is that the system becomes faster, more efficient, more scalable, and less constrained by heat and bandwidth. The revolution may be invisible. A cooler data center, a faster training run, a lower energy cost per inference, a larger model that can be trained without impossible networking overhead. A scientific simulation accelerated because optical hardware handled a bottleneck. That is how light may enter AI, not as a glowing machine in a movie, but as less waste inside the machine we already depend on. Still, we should be careful. Optical AI computing will not erase the energy problem by itself. Generating light costs energy. Lasers cost energy. Modulators cost energy. Detectors cost energy. Analog optical systems need calibration. Thermal tuning can consume power. Optical, electrical conversion can be expensive. Packaging can be complex. Photonic chips must be manufactured with precision. Light does not automatically make a system efficient. A badly designed optical computer can waste power. A system that saves energy in one place may spend it in another. A photonic accelerator that is efficient for one operation may be inefficient for a full workload. The entire system must be counted: source, modulation, propagation detection, diversion, control, memory, cooling, utilization, manufacturing. This is why the field must resist simple slogans. Light is not magic. Light is an opportunity. It offers physical advantages. But engineering decides whether those advantages survive contact with reality. Now, let us turn to quantum dots. Because quantum dots are another way the nanoscale changes light. A quantum dot is a tiny semiconductor crystal, so small that quantum mechanics shapes its optical and electronic behavior. At ordinary scales, a semiconductor has properties determined mostly by its material. At the nanoscale, size itself becomes a control knob. Make the dot larger, and it may emit one color. Make it smaller, and it may emit another. Change composition, shape, shell, or surface chemistry, and the behavior changes again. This is why quantum dots became so powerful in displays. They can produce bright, narrow, tunable colors. A television or monitor using quantum dots can deliver highly saturated reds and greens, improving color performance. That is the consumer face of the technology. Bright screens, better color, more efficient light conversion. But quantum dots are far more than display materials. They are used in biomedical imaging research because they can be bright, photostable fluorescent probes. They can be engineered for sensing. They can interact with chemical environments. They can serve as nanoscale labels. They are studied for solar cells, photodetectors, IDs, lasers, single photon sources, and quantum technologies. A quantum dot can behave almost like an artificial atom. That phrase is important. Artificial atom. Because it means the dot can have discrete energy levels. It can absorb and emit light in controlled ways. It can, under the right conditions, release photons one at a time. And single photons are essential for quantum communication and quantum networks. This is where quantum dots meet the future of information. In ordinary communication, light pulses can contain many photons. In quantum communication, a single photon can carry quantum information. It can be part of a system where measuring it changes it. It can support secure communication schemes. It can help link quantum processors or memories. It can become a building block of a quantum network, but single photons must be high quality, pure, indistinguishable, coherent, generated at useful rates, at useful wavelengths, and compatible with real infrastructure. That last phrase matters. Useful wavelengths. The world already has fiber, optic networks. Those networks work best in telecom bands, where optical fiber losses are low. If a quantum dot source emits beautiful single photons at a wavelength that does not travel well through fiber, the system faces another problem. It may need frequency conversion, extra components, extra noise, extra complexity. So a coherent quantum dot single photon source operating directly in a telecom band is a major step. That is why recent 2026 work in Nature nanotechnology matters. Researchers demonstrated waveguide, integrated indium arsenide quantum dots operating in the original telecom band, known as the O band, roughly from 260 to 360 nanometers. They reported quantum coherent emission with line widths only slightly broader than the lifetime limit, and bright emission rates under pulsed excitation. The technical meaning is important. The photons were not only at a useful telecom wavelength, they were coherent enough to be relevant for scalable quantum networks. This is not the finished quantum internet, but it is one of the components such a future may need. A reliable photon emitter interface on a photonic platform at a telecom wavelength with strong optical performance. That is the kind of detail that turns quantum networking, necking from diagram into engineering. This is the fourth lesson. The quantum future depends on components that are boring enough to manufacture and exquisite enough to preserve quantum behavior. That is the paradox. Quantum systems are delicate. Manufacturing wants repeatability. Telecom networks want stability. Chips want integration. Quantum information wants coherence. The future requires all of them at once. A quantum dot in a lab is not enough. A quantum dot integrated into a waveguide is more serious. A quantum dot emitting coherent single photons in a telecom band is more serious still. A scalable, manufacturable, stable system that can connect quantum nodes over fiber would be another step entirely. This is why quantum dots are so important. They sit at the intersection of materials science, optics, electronics, quantum physics, and nanofabrication. They are not only particles, they are interfaces between matter and light, between classical devices and quantum states, between local chips and long-distance networks, between the nanoscale and the infrastructure of communication. But here too, we must avoid hype. Quantum dots will not automatically give us quantum networks. They must be controlled, positioned, tuned, integrated, protected from noise, coupled efficiently to optical modes, made reproducible across devices, operated at practical conditions, connected to memories, repeaters, detectors, and control systems. A single beautiful emitter does not make a network. A network requires architecture, nodes, links, synchronization, error management, photon indistinguishability, storage routing, standards, security, manufacturing, and systems engineering. The story of quantum dots is therefore not only the story of a tiny crystal. It is the story of how tiny crystals might become reliable parts of much larger machines. That same pattern appears again and again in this episode. Nanophotonics is not only about nanoscale structures. It is about whether those structures can reshape computing systems. Optical AI computing is not only about light. It is about whether light can relieve the energy and bandwidth stress of artificial intelligence. Quantum dots are not only about color. They are about whether nanoscale matter can produce, control, and detect light for displays, medicine, sensing, and quantum communication. The small scale matters because the large system is under pressure. AI needs more compute. Data centers need more bandwidth. Quantum networks need better photons. Displays need better color and efficiency. Biomedical imaging needs brighter and more stable probes. Sensors need more sensitive interaction with light. The future keeps asking matter to become more precise. At the nanoscale, matter answers differently. That is why nanotechnology keeps returning to the center of modern science. Not because small is automatically better, but because small changes the rules. Surface area grows. Quantum confinement appears. Light can be trapped, guided, and reshaped. Electrons occupy different states. Photons interact with structures comparable to their wavelength. Materials become tunable in ways bulk materials are not. The nanoscale is not just a smaller version of the ordinary world. It is a different regime. A place where design can reach into the behavior of light itself. And that may be exactly what computing now needs. Because AI is pushing conventional electronics into a difficult era. The world can build more data centers. But power is not infinite. Cooling is not free. Transmission lines are not instant. Chips are not easy to manufacture. Training larger models cannot remain only a matter of burning more electricity. At some point, intelligence must become more efficient. Not only algorithmically, physically. Better architectures, better memory movement, better interconnects, better packaging, better cooling, better mathematical hardware, better mapping between models and machines. Optical systems may become part of that answer. Not because they make computation free, because they may reduce waste in the operations AI performs most heavily. Parallel linear algebra, high bandwidth communication, low latency interconnects, matrix vector multiplication, data movement across clusters. These are places where light has a credible claim, but the honest future is selective. Photonic AI chips may excel at some workloads and fail at others. They may accelerate inference before training. They may serve specialized layers before whole models. They may appear first in data center interconnects rather than processors. They may work best as coprocessors. They may require model architectures designed for optical hardware. They may depend on new software compilers that understand photonic constraints. The machine may not change all at once. It may hybridize. This is how many technologies mature. The future rarely replaces the past cleanly. It grows through it. Optics will not erase electronics. It will enter where electronics is weakest. Electronics will remain where it is strongest. And between them, new architectures will appear. Photonic electronic AI systems. Quantum dot emitters on photonic chips. Silicon photonics in AI networks. Optical interposers. Metasurface processors. Neuromorphic optical circuits. Quantum light sources. Sensing platforms. Display materials. Biomedical probes. All connected by one deeper movement. The effort to make light programmable at smaller scales. So what are nanophotonics, optical AI computing, and quantum dots truly about? They are about speed. But speed is only the surface. They are about energy. But energy is only the constraint. They are about chips. But chips are only the stage. They are about light, becoming a working material of computation. They are about photons, entering the places where electrons are beginning to struggle. They are about nanoscale structures that bend, guide, split, trap, and tune light. They are about AI systems that may one day compute with less heat and more bandwidth. They are about quantum, dots that turn size into color, nanoscale matter into light, and single photons into possible carriers of quantum information. They are about displays that glow because quantum mechanics has been engineered. They are about sensors and biomedical imaging that use light from tiny crystals to reveal hidden signals. They are about quantum networks that may require coherent single photons at telecom wavelengths. And they are about the possibility that the future of information will be built not only from switches, but from waves. That future is not guaranteed. There are hard problems ahead: noise, precision, memory, manufacturing, integration, packaging, cost, reliability, software, scaling, and proof that these systems beat electronic alternatives where it actually matters. But the direction is clear. As AI grows, the world cannot rely only on making the same electronic systems larger. As quantum networking matures, the world cannot rely only on fragile laboratory setups. As sensing and displays advance, the world will continue to use nanoscale light, matter interactions in more precise ways. The photon is becoming practical. The quantum dot is becoming infrastructural. The nanostructure is becoming computational. That is the quiet revolution. Not light as symbol, light as machine. I'm Ralph Clayton, host of the VTM Podcast. Thank you for joining me for episode 24, and this look into nanophotonics, optical AI computing, quantum dots, and the technologies beginning to reshape how intelligence and information move through the world. And remember, not every faster chip is a better future. Not every beam of light becomes computation, and sometimes the next age of intelligence begins when matter becomes small enough to teach light how to think.